In our exploration of DC analysis of diode circuits, we have seen examples of the breakdown assumption failing. In this video, we'll use this shunt regulator with a Zener diode to analyze a circuit where the diode operates in the breakdown region, so we will see the assumption succeed. But wait, there's more. We also have yet to use the results of our analysis for anything beyond checking the assumption. Shunt regulators suffer from inefficiency. I will use the results to calculate the efficiency under varying source voltages. Let's begin. We are going to annotate the circuit and assume the diode is in the breakdown region. We have not worked with a Zener diode before. Zener diodes have lower, more tightly specified breakdown voltages, but you will see the analysis is no different. The value of interest when working with a Zener is the breakdown voltage. Let's use 5.1 volts and add that to the schematic. We assume the diode voltage is the negative of the breakdown voltage. With a voltage source and assumed voltage across the Zener diode, we write 2 kVLs. For the voltage supply, we get this kVL, and for the Zener, we get this kVL. From these equations, we know the node voltages and may be led to believe that they are not dependent on the value of the load RL. Let's check the assumption by writing a KCL on one side of the Zener. Solving the KCL for the diode current gives us this, which we rewrite in terms of the node voltages, plug in numerical values, and calculate a solution. Notice that this current is dependent on the load, and therefore the validity of the assumption will depend on the load resistance. We now have the operating point. Looking at the VI curve, we see the operating point is feasible for the breakdown region of the diode. This means, under these conditions, the assumption is valid. So why not just put a Zener diode in parallel to any load across which we want to regulate voltage? In a word, efficiency. Let's use the results to calculate the efficiency of this regulator. We need to calculate the power dissipated by the load. We use the numerical results we found while checking the assumption and calculate power delivered to the load. We also need the power supplied. Taking advantage of the fact that the supply is in series with R sub S, we rewrite the source current in terms of the node voltages and calculate the power supplied. Using these results, we calculate the efficiency. Efficiency is the output power divided by the input power. In this case, P sub RL over P sub Vs. And we can see that only 62.8% of the power supplied is delivered to the load. But let's take this a step further. Frequently, students will ask me why bother writing the equations if we can just simulate the circuit. If we get comfortable working symbolically, we can use the equations to develop understanding of dependencies and relationships. Let's try it. We can remove the value of Vs and treat it symbolically. This will lead us to a relationship between the value of the source and the efficiency of the regulator. We write the same equations, replacing the 6.5 volt value with the symbolic variable V sub S. Now, please do the algebra by hand if you'd like. It's good for you. It's like eating vegetables. Or let MATLAB do it for you with code like this. Looking at the output, we see a function for eta as dependent on the value of V sub S. Let's make that easier to read. Then we can plot the relationship. If we naively interpret this plot, we may be led to believe we can achieve free energy. But we know better than that. We can't have an efficiency above 100%. So what's going on? It's important to remember that this analysis is based on an assumption, and that assumption is not true for all values of V sub s. So how do we figure out in which domain this is true? We use the symbolic equations again. This time to find the current through the diode as a function of Vs. The breakdown assumption is valid when the current is negative. So we're trying to find the value where it is no longer negative, aka 0 amps. Let's use MATLAB again to solve for the value of V sub s that makes this true. The output is the border of where the assumption is true. Let's add that to the plot. Above the voltage, the relationship between V sub s and eta is valid. Below the voltage, it is not. If a shunt regulator is so inefficient, why would we use one? It is simple. With only two components, the diode and a series resistor, it's possible to implement a regulator. That simplicity also means low cost. Neither of the two components cost a significant amount. The diode is responsive to changes in source voltage. In fact, this leads to a common use of Zeners as shunt regulators: overvoltage protection. If the time the diode spends in the breakdown region is short, the inefficiency is less of a concern. Finally, the inefficiency may be tolerable if the application is low power to begin with. I hope this video accomplished two things. First, it gave you an example of when the breakdown assumption is correct. Second, it served as a practical example of how this type of analysis is applied to a common circuit. If you've stuck with me this far, the next video will introduce a new wrinkle to the analysis: a circuit with multiple diodes. Until then, stay tuned and good luck.